All right, folks. So welcome to another video on uh, the project for ECE 3710. So last time we left off with our open loop block diagram, right? And we said we're going to be using this model or at least a modified version of this model of the DC motor to implement our controller around that system, because this is our plant, right? And then I left the question with you to decide where the gear ratio would end up, and then make sure the gear ratio that you are using is N2 over N1, as I mentioned in e-learning, because this is basically used as a torque amplifier. Okay, torque amplifier meaning the output torque from the motor, which is the electromagnetic torque after some of the losses, need to be amplified to drive the load that we are working with. So this gear ratio should be placed in at least in one place here in our block diagram, right? And then and I hope you figure this out on your own, but if not, this gear ratio would end up right here. Okay, because this is where we have our torque. This is our electromagnetic torque, TE, right? And then before we pass it on to the mechanical system, that needs to be amplified, okay, by the gear ratio, which is a number that's larger than 1. Each of you have received a parameter that is larger than 1 for your gear ratio. So this would show up in this place and only here, okay, because the rest of the dynamics are described by the mechanical system. And then of course you have your back EMF feeding back into your motor, okay, because the speed determines the back EMF and then that reflects back onto your system. Okay, so that we have discussed already. Again, we are still waiting on the sense again, because we haven't closed the loop yet. So when we do close the loop, I'll let you again think about where that sense again is gonna show up. But today's video is more or less bridging the gap between the model and then developing the reduced order model, or the single transfer function form of your plant, encapsulating the system in Simulink. So basically, how do we take this system and then represent it as a single transfer function relating speed and voltage? Okay, so this is where we are going to be actually addressing and at least directing you what to do in this case. Okay, all right. So now if you look at the e-learning system, you'll see there's another link that shows you how to implement this model in block diagram form without the gear ratio and a couple of different elements, if I remember, but I expect you to implement the complete model for your project. And now moving on to reducing the block diagram, what we do is we have to set the load torque and the friction torque to 0, because essentially those are disturbances in our system. They are treated as disturbances, and since we have a linear system, at least we can assume so, and this way we can actually set those inputs to 0, and then we can find the transfer function between speed and voltage. Okay, so once we set those to 0, this summing junction disappears, and hence we are left with this block diagram. And we've discussed number of times how to reduce such a system to a single transfer function. So I am going to let you do that on your own. And if you have trouble doing this block diagram reduction, please see me during office hours. Okay, so essentially you're going to end up with this single transfer function, and we should be able to verify if this is correct or not compared to our true model, right? So that's what we're going to be focusing on today. So once you have once you have reduced the block diagram again, use a transfer function very similar to this, but this is going to be a little bit more complex. So you'll need to carefully and clearly type these values in so that you can see if your results are matching. So be careful when you type these values in. Okay. Now when we go into the Matlab model, right? So you should see your original model, right? And then of course the reduced single transfer function model should be there. Okay, so this is now we are trying to verify if these two are the same. Okay, so in order for us to do that, we will need to apply the same input. Okay, we're going to apply the same input, and then we're going to look at that output on the scope. Okay, we're going to be looking at the output on the scope. And make sure you've populated all the variables in your workspace. So if you go to Matlab, in the workspace, you'll see that your variables are populated. Okay, so if that's not the case, you may want to have those populated, have a script ready so that you can run those, and that way you can make sure you know it works. Okay, now when you run this, hope it ran. Yeah, there are no errors. Okay, so now it's actually good practice to go and check your Matlab window to see if there are errors or warnings. But when we go in here into the scope, we should essentially see exactly the same result. Okay, exactly the same result, and make sure you are not changing your load during the at least few cycles, because if you change load, these two systems are going to respond differently, right? Because here we have a load and then we are assuming the load is 0. So you can either set this load at a very, after 200 seconds or something like that, very large time. But essentially for this model reduction that I've done, the two systems are matching. So this is another stopping point, another milestone for you to get this verification done, because this block diagram, this transfer function is what we're going to be using to develop your controller using the root locus method. Okay, all right, so more of that to come later. I hope all of you are now following with the project and at this point. And again, if you're not, feel free to reach out. All right. Okay. Thank you, folks.